Hello and welcome to this tutorial on graph traversals. So today we will be discussing about another graph traversal which is known as depth first search or DFS. But before we get started, make sure to check out free masterclasses on Scalar's event page to learn from best industry leading experts. Also, subscribe to our channel if you haven't already. Let's try to understand this algorithm called depth first search or sometimes called as depth first traversal. So it's an algorithm for traversing the graph or searching the graph. It can be used on tree. So on tree, the pre-ordered traversal that you have done, it's actually a depth first search. The algorithm starts at root node. So in case of graph, there is no root node. So you can arbitrarily you can select any node as the root node, and or you can have some specific node, and you have to explore as far as possible along each branch before doing the backtracking. So we'll try to understand this through an example. And of course, this algorithm, since you are doing it recursively, uses extra memory, which is usually a stack. So if you're using a stack, in case of recursion, it will be created automatically. Even if you are doing this algorithm iteratively, you can maintain a stack like data structure and do the work, which is needed to keep track of nodes discovered so far along a specific branch, which helps in the backtracking in the graph. We'll understand this concept when we are running through the algorithm. And this DFS has many applications. Some of the applications I've listed down here. It is used in finding out connected components. You can also use BFS here. Basically, you want to look at what components of the graph they are connected. So for example, if this is a graph, this whole thing is one graph. It has two connected components. So you can do a traversal from this node, which will actually visit this whole component, and you can do a traversal from maybe this node, which will visit this whole component. So we'll do a separate tutorial on connected components. Topological sorting, it can be used. It is also used in finding out bridges in a graph. Cycle detection, it can be used. We'll look at cycle detection in this tutorial. Strongly connected components is a different concept which is used in directed graphs. So DFS again is used there, and it can be used to solve puzzles with only one solution, such as mazes. Maybe you want to find out a path in a maze. Maybe there is only one solution, so you can easily use DFS along with backtracking to find out that particular path. It can be used in maze generation with the randomized DFS algorithm, and it can also be used in finding bi-connectivity in graphs. So let us try to understand the algorithm next. So DFS can also be used on a tree. So if you have this tree, so what this DFS will do, it will start from, let's say, root node. It will go in this direction, here, here, here. Then it will backtrack and it will enter into these branches. So it's just like a pre-order traversal that we have done on trees. But in case of graphs, the situation is little different. Why? Because graphs can contain a cycle. So we have to see what to do in case of a graph. Let us try to understand with the help of this graph how DFS will actually work. Let me draw the adjacency list as well. That will be input, and that is how the graph is actually stored. With 0 we have the neighbors which are 1 and 2. With 1 we have the neighbors 0 and 4. With 2 we have the neighbors 0, 3 and 4. With 3 we have the neighbors 2 and 6. With 4 we have the neighbors 1, 2 and 6. 5 we have only one neighbor, that is 4. With 6 we have two neighbors, that are 3 and 4. So this is how the adjacency list of the graph will look like. Now we need to understand how this DFS is actually going to work. So we are going to start from this node. It can be any node. So I'm going to take 0 as the starting node from the source node. And now since the graph can contain a cycle, I need to maintain a visited array. So I'm just drawing it here. So initially nothing is visited. So this is a visited array 0, 1, 2, 3, 4, 5, 6. So I need this much array, right? I'll call it visited. This will help me to ensure that I do not visit the same node again. If it is already visited, we'll just backtrack, we'll go back. So I start with 0, I said fine. I will mark this as visited, and since it's going to be recursive algorithm, so this node is in the stack. Now 0 can say, okay, what are my neighbors? Neighbor of 0 is 1. So it will pick this node, the first node. I will try to iterate, but first I picked 1, and I will make a DFS recursive call on 1. So I will go to this node. So I'll mark 1 as visited. So 1 is in the stack also. And now from 1, I can go to some neighbors, right? So 1's neighbors are 0. So 0 is already visited, so I will not go here. I will, if I go, I just come back, right? So I say, okay, this, or I will not go. So this node is not visited. This 0 is already visited, so I will not make a call. But what about 4? 4 is visited, so I'm iterating on this list. So 4 is visited, right? So I make 4 is not visited, I make a call on 4. So I go and visit this node 4. So 4 is marked as visited and 4 goes into the stack. So I think on the diagram you should also see a 0 here, right? Before 1 you have a 0, right? So this portion got little cropped out from the screen. So 0 1 4. This is how the stack looks like at the moment. At 4, I again do the same work. I look at what are the neighbors of 4. The neighbor of 4 is 1, which is visited. So don't do any work. The neighbor is 2, which is not yet visited. Now what 4 will do? 4 will visit 2. I'll go and visit this node. So 2 is visited and 2 is now part of the stack. Now at 2, I look at what are the neighbors. The neighbor is 0, which is visited. The neighbor is 3, which is not yet visited. So I go to 3, this node. So I mark this 3 as visited and I come to 3. So what are neighbors of 3? So it is 2 and 6. So 2 is visited, I don't do any work. 6 is not visited. So I go and visit 6. I go here. So 6 is marked as visited. So 3 is in the stack, 6 is in the stack. Right? Now at 6, I look at the neighbors. The neighbors is 3, which is visited. Don't do any work. Another neighbor is 4, which is also visited. So don't do any work. Now what I can do? So 6 is already visited and 6 does not have a neighbor which is not yet visited, right? So what you will do? You will go back. This is important. So this is backtracking. So you come back at 3. So from 6, you are now coming back at 3. So 6 is popped from the stack. Now at 3, you look at, I was running a loop. I was trying to traverse the neighbors and I already went and explored 6. So this is over. So from 3, I cannot go anywhere else. This list is over. So I will just go back. I will backtrack. I will come back at 2. So at 2, I see, okay, I went to 3. 3 is visited. Can I go to 4? 4 is also visited. So I cannot go to 4. So 2's neighbor have been visited. So I can say, okay, let's just go back from 2. I go back to the previous node. So before 2, I came from 4. So I come back at 4. So this is backtracking. Now at 4, I can say, okay, I went to 2, so 2 is visited. What about 6? Oh, sorry, what about 5? So this neighbor is 5 actually. 4 has a neighbor that is 5. 4 has neighbors 1, 2, 6 and 5. 5 and 6 actually. 4 neighbors it has. 1, 2, 3, 4. Yeah, 4 has 4 neighbors. So it will look at 5. Can I visit 5? The answer is yes, I can visit 5. So 4 will make a call at 5. And 5 will say, okay, I am visited now. So if I talk about the order, right? So it was like 0, 1, 2, 3, 6, and then sorry, 0, 1, 0, 1, 4, 2, 3. 0, 1, 4, 2, 3, 6. And now you are actually visiting 5, right? You're now visiting 5. From 6, you come back 3, you come back to 2, come back to 4. And now 4 will say, okay, 4 has a neighbor that is 5. It is not yet visited. It will go and visit it. And 5 will say, okay, I can only go to 4, but 4 is visited. Hence, I will go back. So it will simply return. I go back to 4. Now 4 says, okay, 5 is visited. What about 6? 6 is also visited. 6 is not visited by 4, but it is visited by 3. So it will not go to 6 also. Now 4 says, okay, all my neighbors have been done. I will go back. It will come back at now 1, right? So here after 4, you went to 5. 5 is over. 4 is over. Now you come back at 1. 1 says, okay, all my neighbors have been visited now. I will just pop. I will come back at 0. Now in the stack, you are in this function 0. 0 says fine, all my neighbors. 1 is visited. Now 0 looks at 2. 2 is also marked visited in this array. So it says, okay, my list is also finished. So I'll just go back. So this is also popped off from the call stack. This is how the DFS algorithm works. And given this adjacency list, this will be the output that we will get. So the idea was to traverse all the nodes and this is what we will get by traversing all the nodes. Okay, so I hope you understood the algorithm. Fairly simple. If the graph has multiple different components, then we will see that you need to initiate DFS from one node in each component. Okay, so this is something easy that can be done later on, but first of all we'll focus on this simple DFS algorithm where we are assuming there is only one component. Okay, so we are assuming one component in the graph as of now. So let us code this algorithm next. Let us look at the implementation of DFS in Java. So I already have the graph class which is implemented in the previous tutorials. So in this, I'm going to add a DFS method, and this is going to accept the source node from where I'm going to start the DFS. So I'm assuming there is a single component in the graph. So what I need to do, so firstly I need to build a visited array. That is the data structure we will be needed. So we can keep things simple. We can create a boolean visited array, and this is going to be of size v. That is the number of vertices in the graph. So initially everything will be set to false, and in Java by default a boolean array is false. Now I actually want to do this traversal recursively. So I cannot make this as a recursive function because I cannot create this array again and again in the recursive function. So what I want this array to be shared across all the function calls that I'm making. So for that is why I need to create another function which is going to help this DFS. I can call that as DFS helper, and here I'm going to get the source node or the node, the current node where I am, and the boolean visited array. So this array will be passed and it will be shared across all the function calls, right? So I can simply make call to DFS helper, and I can give source node and the visited array as input to this function. Right now, here what I need to do, as soon as I come to a node, the first thing I will do is I will mark that node as visited. So I can say, okay, I can print out that node, that is fine, and I can say visited of that node, this is equal to true, that yes, I have visited this node. Let us take a small example. Let's say I have 1 2 3 and 4 and 5. Let's say this is the graph. So if I start from this node, so I will mark this as visited, and now I will look at neighbors of 1. So 1's neighbors will be, let's say, 2 and 4. So I'll iterate on this list and I will go to the neighbor which is not yet visited. So right now 2 is not visited, so I'll make a call to 2. Okay, so how do I do it? To iterate on this list, we need to create a list iterator. I think this part was not visible, so I'll just hide myself. What I'm saying is that 1 has neighbors 2 and 4, so I'll make a call at 2 first. So how do I get that? For that I need to create a list iterator first. So I can say fine, let us create a iterator of the type integer. Let's call it it, which is the iterator to iterate on this list. So I can say okay, adjacency list of this node, which is, let's say, 0 source in my case, dot list iterator. So using this iterator we can easily iterate. So while I have items in this list, while it dot as next, what to do? I can say okay, give me the neighboring node. So the neighboring node, this is given by it dot next. So I will now check, is 2 not visited? Yes, 2 is not visited. So how do I check? I check from the array. So 2 is not visited neighbor. Then what to do? I have to make a recursive call. So I can make a call to DFS helper, give it the node is neighbor, and give it the visited array. Right? So I'll show you what's going to happen in this scenario. So I have this, let's say 1 2 3 4 5. So generally in the code the indexing is assumed to be 0 based, but in the example I took it 1 based, but hopefully you will understand that part. So I check 1 is connected with 2 and 4. So 2 is not yet visited. So 1 is visited. So as soon as I come to 1, I mark 1 as visited. Then I iterate over the neighbors of 1. I check 2 is not visited. I make a function call on 2. So 2 is now visited. Now I look at neighbors of 2. So 2 has neighbors which is 1 and 3. So out of this, 1 is already visited. So I don't do any work. So I'll make a call at 3. So as soon as I come to 3, 3 is visited. And 3 has neighbors again 2 and 4. So 3 looks at, okay, 2 is visited. So I'll make a call at 4. At 4, I have again neighbors which are 1 and 5. So 4 says, okay, 1 is visited, don't do any work, make a call at 5. So 4 visits 5. So 5 is now visited. Now 5 has only one neighbor, 4, which is visited. So this loop will not run for 5 because it will iterate on 4 and 4 is already visited. So this if will not execute and while will not do any work. So you will simply return, right? So from here, we will come back. So you come back here, right? Now at 4, you see 5 is done. So list of 4 is also finished. So this loop is over. So 4 goes back to 3. So 3 says, okay, I can go to 4. This is also done. So 3's loop is also over. You go back at 2. So at 2, you have gone to 3. That's also done. Now suppose there was a node 6 here, right? So what will happen now? 2 will say, okay, yes, I can go to 6. So 2 will go to 6 and 6 will get visited and you will come back, right? And of course, these nodes are also marked visited. This loop is also now over. Now at 2, you will say, okay, my list is done. I will go back. It will go back here. Now 1 will look at, okay, can I go to 4? But 4 is already visited. Hence, you do not go. You do not make a call at 4. So this edge is not considered. And at 1, you can say, okay, this list is done because 4 is also visited. And hence, I go back. This is how it will go back into the main. So in this case, the output would look like 1, 2, 3, 4, 5, and then you have gone to 6 as well, right? This is how the DFS is going to get performed using this code. Now let us test our code. Does it work fine or does it work as expected? So you have understood DFS on graphs. Next thing we will learn is how do we do cycle detection on graphs. Basically, we will do this algorithm of cycle detection on two types of graphs. One is on undirected graph, which is given here, and secondly we will do it on directed graphs in which the algorithm will change a little bit. This graph is an example of a undirected graph. So now how do I detect a cycle in this? So I can use BFS or DFS, right? So if you remember, the fundamental difference between a tree and a graph is that a tree is always not containing a cycle. Tree does not contain a cycle, but every tree is also a graph. Basically, if you have a cycle in a tree, it becomes a graph, right? And every tree is also a graph. So if I give you an example, let's say this is node A, it is connected with B, and it is also connected with C. So right now it is a tree, right? And it is also a graph. But if I add this edge, it definitely becomes a graph, right? It is not a tree now because it contains a cycle, right? So now what is the significance of cycle, or how do we detect a cycle? So it is pretty easy. Let's say I start traversing this using any algorithm, let's say BFS or DFS. Let's say I start with A and I make a DFS call on its child, that is B. At B, I make a DFS call on its child C, and C will now look at its neighbors. So it will see, okay, I discovered a neighbor, right? Now C has two neighbors. So one of the neighbor is, let's say, B, right? So if C looks at B, right? B is already visited. But is it really a cycle? The answer is no. I cannot say that this edge is going to create a cycle. The answer is no, right? Let's say there is one more edge from C to D. C makes a call at D and it visits D. Is this edge causing a cycle? Basically, the answer is again no, right? So what is the difference between this edge, right? So basically, before visiting D, D was undiscovered. D was not visited, but B was discovered. B was discovered. Now suppose I create one more edge, which is this edge, right? So if I now C makes a DFS call on, let's say, A, right? But as soon as I make this call, I see, okay, I'm landing at a node which is visited, and I can say it is a cycle, right? it is a cycle, right? So basically what I'm trying to say is that B was also visited, D was not visited. So here we are sure there is no cycle. But here the answer is no, because B was discovered, but it was parent of C. It was parent of C, right? It was parent of C. Whereas from C, when you go to A was already visited and A was not the parent of C. A was not the parent of C in the DFS call. So this is the condition, that if we encounter a node which is already visited and it is not the parent of the current node, then we can definitely say yes, there is a cycle that is present, right? So let me dry run this algorithm on this graph. So let us create a adjacency list. So 0 is connected with, let's say, 1 and 2. 1 is connected with 0 and 4. 2 is connected with 0, 3 and 4. Then 3 is connected with 2 and 6. Then 4 is connected with 1, 2 and 6. Then 5 is connected with just 4 and 6 is connected with 3 and 5, right? Now suppose I start doing a DFS from node 0 and I want to check if there is a cycle or not. So I start from this node 0. I said okay, go and make a call at its neighbor. So 1 is the neighbor, it is not visited. So right now my goal is to iterate on this, but I make a DFS call on the first node that is not visited. So 1 is not visited, I go here. Now at 1, I look at the neighbors. The neighbor is 0. But if you look at 0, 0 is already visited. 0 is visited, but 0 is also the parent of 1. So hence we have to skip this node. We will not do anything at 0. What about 4? 4 is not yet visited. So I go and make a DFS call at 4, right? Now we come at 4. 4 is now marked as visited. 1 is visited, 0 is visited. 4's neighbor is 1. So I will not do any work. Like C's neighbor is B. B is visited. 1 is visited, but 1 is parent. So we will skip it. What about 2? 2 is not yet visited. So I can go at this node and I can mark it as visited, right? Now look at 2. Now 2 has a neighbor that is 0. Now this is an interesting case. Okay. So 2 has a neighbor that is 0. So I will draw this edge separately. I'm going to mark this edge in red. So 2 says, can I go to 0? Now what is the condition at 0? 0 is already visited, right? And 0 is not the parent of 2, right? So basically you are hitting this edge. We will call this edge as a kind of a back edge, right? So it is taking us back in the same path from where we started, or to one of the ancestor nodes. Okay. So it is an edge from the current node to some ancestor node. Why ancestor? Because if you look at the path that we have traced is 0, 1, 4, 2, and then from 2 we are going back. We are going at 0. This is like a back edge, right? Now, as soon as I get this edge, it will be the terminating case, right? So at this point, I can directly say without looking at the rest of the graph, yes, there is a cycle. So this is going to return true. Okay, so I'm going to say, okay, I'm going to return a true from this node 2. So this true will be told back to 4. Okay, so 2 will say, okay, that yes, I found a cycle. Okay, so what 4 would have said that, okay, I do not see a cycle I am not seeing the cycle as of now, but let me call a neighbor and check if it can discover a cycle. So 2 discovered a cycle. So that true is returned to 4. 4 will also return true. 1 will also return true, and 0 will also return true, right? Because it's going to be a stack based algorithm. So this true will be propagated back to the main in this manner, right? So there will be a base case, there will be a recursive case. So let us try to write the code and understand this algorithm in little more detail. So let us write the code for cycle detection. So I'm going to make a boolean method, which is, let's say, detect cycle, and here I need to give some source node from where I want to start, right? Or you can take 0 as well, right? So we are assuming that the nodes are numbered from 0, and we can ignore this source. We can directly give 0 as well, right? So now since it's going to be a recursive function like DFS, right? So one thing we did in DFS was we maintained a visited array. So we also need to maintain a visited array that will tell whether a node has been visited or not. So boolean visited, this is equal to new boolean, and the size is, let's say, v, right? So by default this visited array is set to false in Java, so I'm not explicitly setting it. And here I can say, okay, I'm going to create a helper method, detect cycle helper, and I'm going to give it a node, let's say 0, and I'm going to give it the visited array, right? So this method is just like a wrapper function, because we need to create the visited array, and this needs to be shared across all function calls. So we are going to make a helper method, boolean detect cycle helper. It's going to accept the node, and second thing it's going to accept is the boolean visited array. So now here we will return some true or false, right? So let's see how this is going to be. So first of all, when you're encountering a node for the first time, so definitely you should mark that node as visited. So visited of node, this is equal to true. Next thing you will do is you will iterate over the adjacency list of that node, and you will make recursive DFS calls, right? So let's see how we can do it. So just like before we have done here, right? So I'll show you. So you will create a iterator to iterate on that node, right? Or like in DFS, right? Something similar we will do, right? So I'll just copy this node code, and I'll show you what modifications you need to make in the DFS code, right? So here we go. So we have created an iterator to iterate over the adjacency list of the given node. And then what I'm saying, I'm finding out the neighbor, right? So if the neighbor is not visited, now here the call will be different. Okay. So if the neighbor is not visited, I will go and visit that neighbor, and I will also store the result what that neighbor is saying. For example, let's say 1 is connected with 2, 2 is connected with 3, 3 is connected with 4, and 4 is again, let's say, connected with 1, right? So I will make a call at 2, that is the neighbor. Now this 2 is supposed to return some result back to 1, right? So that result can be true or it can be false. So 2 might have called 3, 3 might have called 4, 4 might have called 1. Oh, and here it saw, yes, there is a cycle. So true, 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 that will get propagated back, right? So if the neighbor is not visited, definitely we have to go and check that, okay, yes, is there a cycle at that node or not? I can say, okay, Boolean, I can say um, cycle found, right? Something like this. So they did find a cycle in few in that part of the graph, right? So here I can make a call to detect cycle helper, and here I can give the node, which is going to be the neighbor, and I'm going to give the visited array, right? Now this is like a recursive case. You called some node, that node said, yes, I found the cycle. If the answer is true, if cycle found is true, you can directly return true from this point without iterating on the remaining adjacency list of the current node, right? And there is one more scenario that can happen outside this if, right? Outside this if, so it's like a recursive case I've written here. So this is like a recursive case. There can also be a base case, right? So base case would be that you are hitting a node which is already visited, right? So I can say else if visited of neighbor, this is true, right? This is true, right? And there is one more condition, right? So I'm basically saying something like this. 1 is connected with 2, 2 is connected with 3, 3 is connected with 4. And now you said, okay, I came to this node, I came to this node, I came to this node. From 4 to 1, there is an edge. So as soon as you discover this edge, that fine, I am going to a neighbor which is already visited, and this 1 is not the parent of 4. Okay, so 4's neighbor is also 3, but 3 is the parent of 4. So you cannot say about cycle at this node. Okay, but you can say about cycle because of this edge. The 4 is taking me to the 1 which is not the parent, right? So you can say the neighbor that we have discovered is not equal to parent of 4. But how do we get parent of 4? That is a question. Okay, so this is the neighbor, right? So that means, and this is the parent. So we want that this neighbor that we are discovering should not be same as parent, because force neighbor is also 3, right? If it is 3, then we cannot say anything, right? We have to skip this. But this neighbor, if it is not same as parent, then yes, definitely there is a cycle. But how do I find the parent of current node, right? So that is a question. This parent we will have to maintain in the function call by passing one more parameter, right? So parent, and here we have to, so when you discovered this neighbor, right, the parent of this neighbor is going to be the current node, right? So this will be node. So I'm setting the parent here. If neighbor is not equal to parent, then I can say return true, right? Since I'm using a else if condition here, right? So this else if will be only executed if the node is already visited, right? So if it is not visited, it will go here, but if it is visited, it will come here. So that means writing this part is optional. So I can just remove this, and I can just simplify the condition to be only this: neighbor is not equal to parent. I'm going to return true. But if I come outside the while loop, that means I could not detect any back edge, right? So this is actually the point where we are detecting the back edge, and this is actually the recursive case. This if condition is a recursive call, that's it, right? So this is kind of a base case that we found a back edge, right? Otherwise, if we could not find any back edge, we are going to return false from that node. So I think this function looks good to me. Now we have to give a parent here as well. So parent of the source node, we can just set it to -1, no parent, right? And let us dry run this code, and let us also test the functionality first. So here in the main, I have this file. So I have created a graph. I have done the DFS, simple DFS works, but now I want to S out about the cycle detection. So if g dot detect cycle, you can just see out, S out, yes, there is a cycle. Else you can say S out, there is no cycle. Let's go and run this code. So let's see what output do we get. So it says yes, there is a cycle. So I'll show you, this is the same graph that we have in the figure. So yes, it contains a cycle. So let me dry run this code for you once again. I'll do it on a smaller graph. Let's say the graph looks like this: 0, 1, 2, 3, 4, and let's say this is the edge, right? So you start from 0, so parent is -1. So you look at neighbors of 0, right? So you said, okay, visited of node, this is true. So this is marked as visited. Then you iterate over the neighbors. So neighbors of 0 are 1, 2, 1 and 3. First we will go to 1. 1 is not visited. So we make a recursive call and ask, did you find a cycle? So 1 is now marked as visited. And when I marked 1, so I said the parent of 1 as the node. So this was the node, this was the neighbor. So neighbor's parent is going to be the node. So parent is 0. So 1's parent is marked as 0. And again, same story repeats. At 1, what do? I make a recursive call. So I ask neighbor of 1, right? Now 1 has 2 neighbors. One of the neighbor is 0. 0 is visited. But what happens here? Is this condition true? What is the neighbor? Neighbor of 1 is 0. What is parent of 1? That is also 0. So we do not execute this else if block. So we basically ignore this case. Okay, we do not do any work here. Then we look at the second neighbor. So 1 has neighbors that are 0 and 2, right? So nothing happens here. What about 2? So 2 is not visited. So we make a recursive call, right? So we go to this node, we make a recursive call. Now 2 is marked as visited. Parent of 2 is 1. Now 2 also has 2 neighbors. 2 has a neighbor that is 1 and it has a neighbor 3. So I do not, if I look at 1, 1 is already visited, right? So I come into this else if. Okay, if it is not visited, I go here, but if it is visited, I come here. So what is the neighbor of 2? That is 1. What is parent of 2? That is also 1. So this condition is also not true. So I do not do anything here. So nothing happens here. We talk about this edge 2 to 3. So I go to 3. Now at 3, what happens? 3 has two neighbors, 0 and 4. So I go to 0. Is 0 visited? Yes, 0 is visited. So I do not go into this if block, I come into this else block. What is the neighbor, right? So what is now the neighbor of 3? So the neighbor of 3 that I'm considering here is, because of this edge, that is 0. What is the parent of 3? The parent of 3 is actually 2, right? So they are not equal. Yes, 0 and 2, they are not equal. That means yes, return true. So without looking at this part of the graph, 3 returns are true, right? Now 2 got to know, yes, there is a cycle found. So 2 also returns are true. It goes back. 1 also gets to know, yes, there is a cycle found. So as soon as it gets a true, it returns a true. 0 gets to know, yes, there is a cycle, it returns a true back to the main. So this is how this algorithm is working, and I hope you understood it. Now we will talk about cycle detection in case of directed graph. So in case of directed graphs, not just the structure of the graph, but the direction of edges also decide whether there is a cycle or not. If you look at this example, the edges are like this, and if you start from A, you can go to B, you can go to C, but from C you are not able to go to A, right? And of course there is no loop present here, right? So hence there is no cycle. But if I change the direction of the just this edge, I reverse it, right? I can go from A to B, B to C, and from C I can again go back to a node. I can go in a cycle. So hence yes, there is a cycle, right? So now I will tell you, if you use the same algorithm which you used on undirected graphs, what is the problem you're going to face, right? It's not going to work in the same manner. So let me take up one more example. Let's say the graph is like this. Let's say A. From here we have B. Let's say C, D, E, F, and let's say this is connected like this. And let's say I have G, and it is connected with, let's say, C, right? Now suppose you start doing DFS from A, and you say if I hit a node which is already visited, I will say there is a cycle. This is the logic we did in the undirected graph. So let's say you started doing DFS, you started from A, you went to C, okay, from C you went to D, from D you went to E, from E you went to F, and from F you cannot go anywhere else. So you come back and you say, okay, no, there is no cycle. So you come back, you return false, right? And from E again you come back, D, you again come back at C, and again you come back at A, and from A you come back at B. Now you go to V, B is not visited, right? From B you go to G, and from G you go to C, and now you see that I am going to a node that is already visited, this edge, right? And it is C. C is not the parent of G. That means I'm going back in the path. But is it really a cycle? My question to you is it really a cycle? The answer is no. If you start traveling from A, you can come to C, and you cannot get stuck into cycle. From C you can go to E, right? So this is not a cycle. Or you can go to D, right? You can go this way. So this is again a case of non-cyclic graph, right? But if you run the previous algorithm that we executed on a directed graph, it is going to say yes, there is a cycle, because from G you discovered a node which is already visited, right? Hence we need to fix this algorithm, right? So we need to fix the algorithm for directed graph, for directed. Now the question is, how do we fix it, right? So thing is, we need to again detect back edges correctly, right? So from G to C, this is not a back edge, right? I will tell you what is a back edge in case of a directed graph. So back edge is a edge that takes you back to from one of the node to some ancestor node in the same path, right? From the current node to some ancestor, right? Ancestor. So let us take another example inspired from this graph only. Let's say I have A, I have C, I have F, I have D, and I have E, and I have F. Then I have, let's say, B. Then I have, let's say, G, and then I'm pointing to, let's say, C. And let me add one more edge in this graph. So this graph, this edge maybe looks like this. Let's say the edge is like this. Do you see a cycle here? The answer is yes, there is a cycle, right? Or let me add two more nodes, right? Let me add a node, let's say H, and let me add a node. That's it. Let's say one more node I have added. Now, in this part of the graph, there is no cycle. But yes, in this part of the graph, there is a cycle because you can revolve in this path again and again, right? So let us try to see what is a back edge in this scenario, right? So let's say we started doing DFS from A, I went to C, from C I went to D, I went to E, from E I went to F, from F I cannot go anywhere, so I will just come back, right? So what is the state of the call stack? The call stack has A, it has C, it has D, it has E, it has F. Now F says I cannot go anywhere, so I'm just going to return false. So false is propagated back. Then E says, okay, I cannot go anywhere else, I will come back. D says I cannot go anywhere else, I'll come back. C says I cannot go anywhere else, I come back to A. Now A says, okay, let us go to B. So B goes into the stack. B says, let's go to G. G goes into the stack. Now from G I can go to C. C is already visited. But is it a back edge? The answer is still no, right? Because in the current path, right? So if G is giving me a edge that is pointing back to one of the ancestor in this call stack, only then it will form a cycle, right? So the answer still here is no. So I will not take this edge. So can I go anywhere else? Okay. So basically, what is the condition I'm going to check here? So when I'm checking G to C, C is visited. C is visited, but C is not in the stack. C is not in the stack. That means I came to G via path which does not include C. Okay, it is not in the stack. That is the important condition, right? Now G can say, okay, let me go to H. H is not visited, fine. H goes into the stack. Now H says I can go to A. So what happens here? We are going to a node that is visited, and that is also in the current path, right? That means from H I can go to A. From A, if you A again, you can go to H, A, B, G, H. So that means these nodes will form a cycle, A, B, G, H, right? What is the condition to detect a back edge? So I will say, okay, in this DFS traversal, this edge from H to A, this is forming a back edge, right? Because I'm going back to one of the ancestor nodes, right? So the condition is from the current node to some ancestor which is in the stack. We have to check two things. We have to check that this node A is visited and A is also present in the stack. A is in the stack, right? So if both of the conditions are met, we can say yes, there is a cycle, and recursively H will propagate back. So H knows yes, there is a cycle. G knows yes, there is a cycle. B says yes, there is a cycle, and A also tells back yes, there is a cycle. So this is propagated back. There is a cycle. So again, this can be implemented recursively, but how do you check whether A is in the stack, right? So we cannot directly look at the recursive stack. So what you have to do is you have to maintain another data structure. Either you can maintain a hash map or you can simply maintain a array, right? So whenever you are hitting a node, you mark it as visited. Okay, so when I hit A, so these nodes will remain visited, right? But when you're going back, okay, when the nodes are getting popped from the stack, you can remove that node from the stack array also, right? So I can simply create an array called in stack. So if you're visiting a node, next you can mark that yes, it is visited. But when you're going back, you're backtracking. For example, when you went back from C, you can say yes, this node is not in the stack, right? So you have to maintain two boolean arrays, one for visited, one for stack. While backtracking, you will unmark from the stack array, right? So I'll write the code first, then we will do the dry run. But I hope you understood the concept. that here just being visited is not sufficient. We also have to check whether the node is in the stack or not, right? So this is the main tweak that we will use in this algorithm.